Welcome to our deep dive into two foundational machine learning techniques, k-means clustering and principal component analysis, or PCA. In this video, we'll break down these concepts, explore how they work, and see where they fit in the broader landscape of machine learning. Whether you're a beginner or looking to refresh your knowledge, you'll find clear explanations and practical insights. Let's start by understanding what machine learning is and why unsupervised learning methods like k-means and PCA are so important for data analysis. Supervised learning is a branch of machine learning where the algorithm learns patterns from unlabeled data. Unlike supervised learning, there are no predefined outputs. Instead, the goal is to discover hidden structures or groupings within the data. K-means and PCA are two of the most widely used unsupervised learning techniques. K-means helps us find clusters, while PCA helps us reduce the dimensionality of our data. Both are essential tools for making sense of complex datasets. K-means is a clustering algorithm that partitions data into k distinct groups based on similarity. The k in k-means stands for the number of clusters you want to find. The algorithm assigns each data point to the nearest cluster center, called a centroid. Over several iterations, these centroids are updated to minimize the distance between points and their assigned centroid. The result is a set of clusters where each point belongs to the group with the closest mean value. The k-means algorithm follows a simple yet powerful process. First, you choose the number of clusters, k. Next, the algorithm randomly initializes k centroids. Each data point is then assigned to the nearest centroid, forming clusters. The centroids are recalculated as the mean of all points in each cluster. This process repeats until the centroids no longer change significantly, indicating that the clusters have stabilized. The final result is a set of well-defined clusters in your data. Selecting the optimal number of clusters, k, is a critical step in k-means. Too few clusters can oversimplify your data, while too many can make the results noisy and less meaningful. One common approach is the elbow method, where you plot the sum of squared distances for different values of k and look for the point where the decrease slows down, forming an elbow. This point often represents a good balance between simplicity and accuracy. Imagine you run a retail business and want to segment your customers based on their purchasing behavior. By applying k-means clustering to your sales data, you can identify groups of customers with similar buying patterns. This allows you to tailor marketing strategies for each segment, improving customer satisfaction and boosting sales. K-means is widely used in customer segmentation, image compression, and even in organizing documents by topic. K-means is popular because it's simple, fast, and scalable to large datasets. It works well when clusters are spherical and roughly equal in size. The algorithm is easy to implement and interpret, making it a go-to choice for many clustering tasks. However, it's important to remember that k-means assumes clusters are similar in size and density, which may not always be the case in real-world data. Despite its strengths, k-means has some limitations. It struggles with clusters of different shapes and sizes and is sensitive to outliers. The algorithm can also get stuck in local minima, meaning the final clusters depend on the initial placement of centroids. Additionally, you must specify the number of clusters in advance, which isn't always straightforward. Understanding these limitations helps you decide when k-means is the right tool for your data. Let's visualize how k-means works with a simple example. Imagine plotting data points on a two-dimensional graph. The algorithm starts by placing k centroids randomly. Each point is assigned to the nearest centroid, forming clusters. The centroids are then recalculated, and the process repeats. Over time, the clusters become more defined, and the centroids settle into their final positions. This iterative process is what makes k-means both effective and intuitive. K-means is used in a wide range of applications. In marketing, it's used for customer segmentation. In computer vision, it's applied to image compression and color quantization. In document analysis, k-means helps organize large collections of text by topic. Its versatility and speed make it a valuable tool for any data scientist or analyst working with large, unlabeled datasets. Now that we've explored k-means clustering, let's shift our focus to another powerful unsupervised learning technique, principal component analysis, or PCA. While k-means helps us find groups in data, PCA is all about simplifying complex datasets by reducing their dimensions. This makes it easier to visualize and analyze high-dimensional data, which is common in many real-world scenarios. Principal component analysis, or PCA, is a dimensionality reduction technique. It transforms a large set of variables into a smaller one that still contains most of the information in the original set. PCA does this by identifying the directions, called principal components, along which the data varies the most. By projecting the data onto these components, we can reduce the number of dimensions without losing significant information. High-dimensional data can be challenging to analyze and visualize. PCA helps by reducing the number of variables, making patterns easier to spot. It also helps remove noise and redundant information, improving the performance of other machine learning algorithms. PCA is especially useful when you have many correlated features, as it combines them into a smaller set of uncorrelated components. The first step in PCA is to standardize the data. This means adjusting the values so that each feature has a mean of 0 and a standard deviation of 1. Standardization is important because PCA is sensitive to the scale of the data. Features with larger scales can dominate the principal components if not standardized, leading to misleading results. After standardizing the data, the next step is to compute the covariance matrix. This matrix captures how each feature varies with every other feature. The covariance matrix is the foundation for identifying the directions of maximum variance in the data, which will become our principal components. The third step in PCA is to calculate the eigenvectors and eigenvalues of the covariance matrix. Eigenvectors represent the directions of maximum variance, while eigenvalues indicate the magnitude of variance in those directions. By ranking the eigenvectors by their eigenvalues, we can identify the most important directions in the data. Once we have the eigenvectors and eigenvalues, we select the top principal components. These are the directions that capture the most variance in the data. By projecting the original data onto these components, we reduce the number of dimensions while retaining most of the information. This step is crucial for simplifying complex datasets. After applying PCA, you can visualize your data in 2 or 3 dimensions, even if the original dataset had many more features. This makes it much easier to spot patterns, clusters, or outliers. Visualization is a powerful way to communicate insights from high-dimensional data, and PCA is one of the best tools for this purpose. Suppose you're analyzing gene expression data with thousands of features per sample. Visualizing this data directly is nearly impossible. By applying PCA, you can reduce the data to just a few principal components, making it possible to plot and interpret. This approach is widely used in genomics, image processing, and finance, where datasets often have many correlated variables. PCA is valued for its ability to simplify complex datasets, reduce noise, and reveal hidden patterns. It helps improve the performance of other machine learning algorithms by removing redundant features. PCA is also computationally efficient, making it suitable for large datasets. Its ability to transform correlated features into uncorrelated components is especially useful in many scientific and business applications. While PCA is powerful, it has some limitations. It assumes linear relationships between variables and may not capture complex, nonlinear patterns. PCA also requires that the principal components be orthogonal, which may not always align with the true structure of the data. Additionally, interpreting the transformed components can be challenging, as they are combinations of the original features. PCA and kmeans serve different purposes in machine learning. PCA is used for dimensionality reduction, helping to simplify data and reveal patterns. Kmeans, on the other hand, is used for clustering, grouping similar data points together. While both are unsupervised techniques, they address different problems and are often used together to pre-process and analyze data more effectively. In practice, PCA and kmeans are often used together. First, PCA reduces the dimensionality of the data, making it easier to visualize and process. Then, kmeans is applied to the reduced data to find clusters. This combination improves clustering performance and helps avoid issues caused by high-dimensional data, such as the curse of dimensionality. Typical workflow starts with data preprocessing, followed by PCA for dimensionality reduction. After reducing the data to a manageable number of components, kmeans clustering is applied. The results are then analyzed and visualized, often revealing clear groupings that were hidden in the original high-dimensional data. This workflow is common in fields like bioinformatics, marketing, and image analysis. Let's say you have customer data with dozens of features, from purchase history to website interactions. Applying PCA reduces the data to a few principal components, making it easier to visualize. Then, kmeans clusters the customers into distinct groups. This approach helps businesses target marketing efforts and personalize customer experiences more effectively. In image processing, PCA can reduce the number of colors or features in an image, compressing it without significant loss of quality. Kmeans can then be used to group similar pixels, further reducing file size. This combination is widely used in digital photography and computer vision to store and transmit images efficiently. In genomics, researchers often work with datasets containing thousands of gene expression levels. PCA helps reduce the data to few components, making it possible to visualize and interpret. Kmeans can then cluster samples based on genetic similarity, aiding in disease research and personalized medicine. Before applying PCA or kmeans, it's important to pre-process your data. This includes handling missing values, scaling features, and removing outliers. Proper pre-processing ensures that both algorithms perform optimally and that the results are meaningful. Always standardize your data before PCA and consider normalizing before kmeans. After clustering with kmeans, it's important to evaluate the quality of your clusters. Common metrics include the silhouette score, which measures how similar points are within a cluster compared to other clusters. Visualizing the clusters using PCA-reduced data can also help assess whether the groups make sense and are well separated. To evaluate PCA, look at the explained variance ratio for each principal component. This tells you how much information each component retains from the original data. Ideally, a few components should explain most of the variance, allowing you to reduce dimensions without significant information loss. A common mistake with kmeans is choosing the wrong number of clusters. Another pitfall is failing to scale your data, which can skew results. Kmeans also assumes clusters are spherical and similar in size, so it may not perform well on more complex data structures. Always visualize your clusters and experiment with different values of K. With PCA, a common issue is misinterpreting the principal components. Remember, these are combinations of original features and may not have a straightforward meaning. Also, PCA only captures linear relationships, so it may miss important nonlinear patterns. Always check the explained variance and be cautious when interpreting results. For datasets with nonlinear relationships, kernel PCA extends the basic PCA by using kernel functions. This allows it to capture more complex patterns in the data. Kernel PCA is useful in image recognition, bioinformatics, and other fields where linear PCA falls short. There are several variants of kmeans designed to address its limitations. For example, kmethods uses actual data points as cluster centers, making it more robust to outliers. Mini-batch kmeans processes data in small batches, improving speed for very large datasets. Choosing the right variant depends on your data and specific needs. Popular machine learning libraries like scikit-learn and Python provide easy-to-use implementations of both kmeans and PCA. These tools allow you to quickly apply these algorithms to your data, experiment with parameters, and visualize results. Other platforms, such as R and matlab, also offer robust support for these techniques. Interpreting the results of kmeans and PCA requires both technical understanding and domain knowledge. For kmeans, examine the characteristics of each cluster to draw meaningful conclusions. For PCA, analyze the loadings of each principal component to understand which features contribute most to the variance. Combining these insights leads to better decision-making. Effective visualization is key to understanding the output of kmeans and PCA. Scatter plots, heat maps, and 3D projections are commonly used to display clusters and principal components. Visualization not only helps in interpreting results, but also in communicating findings to others, making your analysis more impactful. When working with very large datasets, scalability becomes important. Mini-batch kmeans and incremental PCA are designed to handle big data efficiently. These algorithms process data in chunks, reducing memory usage and computation time. This makes it possible to apply clustering and dimensionality reduction to millions of data points. As with any machine learning technique, it's important to consider the ethical implications of using kmeans and PCA. Ensure that your data is representative and that clustering does not reinforce biases. Be transparent about how you process and interpret data, especially when results impact people or critical decisions. The fields of clustering and dimensionality reduction are evolving rapidly. New algorithms are being developed to handle more complex data types, such as graphs and time series. Advances in deep learning are also influencing how we approach unsupervised learning, with techniques like autoencoders offering alternatives to PCA. Recap: kmeans is a fast and simple clustering algorithm that groups data points based on similarity. It's widely used in customer segmentation, image compression, and document organization. While it has some limitations, understanding its strengths and weaknesses helps you apply it effectively to your data. PCA is a powerful tool for reducing the dimensionality of complex datasets. It helps reveal patterns, remove noise, and improve the performance of other algorithms. By understanding how PCA works and when to use it, you can unlock new insights from your data.